5. Secondary indexes. When you need to perform queries on attributes that aren't a part of a table's primary key, you can use a secondary index. With a secondary index, you can query the data in the table by using an alternate key, in addition to queries against the primary key. In addition to the alternate key attributes and primary key attributes, a secondary index contains a subset of the other table attributes. When you create an index, you specify which attributes will be copied or projected from the base table to the index. At a minimum, DynamoDB projects the key attributes from the base table into the index. DynamoDB supports two types of secondary indexes: global secondary indexes and local secondary indexes. A global secondary index has a partition key and a sort key, which can both be different from the keys in the base table. This type of index is considered global because queries on the index can span all the data in the base table across all partitions. A global secondary index has no size limitations. It also has its own provisioned throughput settings for read-write activity that are separate from the throughput settings of the table. A local secondary index has the same partition key as the base table, but a different sort key. This type of index is considered local because every partition is scoped to a base table partition that has the same partition key value. As a result, the total size of index items for any one partition key value can exceed 10 gigabytes. Also, a local secondary index shares provisioned throughput settings for read-write activity with the table. Each table in DynamoDB can have up to 20 global secondary indexes per table by default and up to 5 local secondary indexes per table. The slide shows an example of when to use a global secondary index. Suppose that you have a music table. You can query items by artist, the partition key, or by artist and song title, the partition key and sort key. What if you also want to query the data by genre and album title? You cannot do this with the music table itself. However, you can create a global secondary index by using genre and album title from the base table. Then query the index in much the same way that you would query the music table. In the index, genre is the partition key and album title is the sort key. Notice that the combination of genre and album title might not be unique. Multiple albums can belong to one genre. Suppose that you want to query by artist and album title. In this case, you would create a local secondary index from the base music table. The local secondary index has the same partition key as the base table, artist, but a different sort key, album title. For a local secondary index, the partition key is the same as the table's partition key. The sort key can be any scalar attribute. Here are the key takeaways from this section of the module. Secondary indexes contain a subset of attributes and an alternate key or keys to support query operations. Global secondary indexes have different partition keys and sort keys from the keys in the base table. Local secondary indexes have the same partition key as the base table, but a different sort key. That's it for this video. Thanks for watching, and I'll see you in the next video. Section 6. Read-Write Throughput. DynamoDB automatically replicates your data across multiple availability zones in an AWS region, which provides built-in high availability and data durability. All copies of your data are usually consistent within a second after a write operation. DynamoDB supports eventually consistent and strongly consistent reads. Eventually consistent is the default. It means that when you read data from a DynamoDB table, the response might not reflect the results of a recently completed write operation. The response might include some stale data. If you repeat your request after a short time, the response should return the latest data. This type of consistency is usually acceptable for use cases such as blogs. If the use case absolutely requires the latest data, use strongly consistent reads. This means that DynamoDB returns a response that reflects the updates from all prior successful write operations. This type of consistency is important for applications such as scoreboards and booking systems. Note that a strongly consistent read might not be available if a network delay or outage occurs. In addition, consistent reads are not supported on global secondary indexes. You can specify the desired consistency level for reading data. DynamoDB transactions simplify the developer experience of making coordinated all-or-nothing changes to multiple items, both within and across tables. With transactions, all steps in a process must complete successfully. If any step fails, you must roll back all changes that were part of the transaction. Transactions provide atomicity, consistency, isolation, and durability, also called ACID, in DynamoDB. ACID transactions help you maintain data correctness in your applications. Use cases for using transactions include processing financial transactions, fulfilling and managing orders, building multiplayer game engines, and coordinating actions across distributed components and services. DynamoDB supports both provisioned and on-demand throughput. Provisioned throughput is the maximum amount of capacity that an application can consume from a table or index. If your application exceeds your provisioned throughput capacity on a table or index, it's subject to request throttling. DynamoDB divides throughput evenly among partitions. The throughput per partition is the total provisioned throughput divided by the number of partitions. This means that if a majority of the reads or writes all occur on a single partition, you will not get the full throughput configured for the table. With provisioned throughput, you specify the throughput capacity in terms of read capacity units, called RCUs, and write capacity units, called WCUs. A read capacity unit, or RCU, is the number of strongly consistent reads per second of items that are up to 4 kilobytes in size. Eventually, consistent reads use half of the provisioned RCUs, meaning that one eventually consistent read requires half an RCU. A write capacity unit, or WCU, is the number of 1 kilobyte writes per second. When you don't know how much throughput is needed, you can use on-demand throughput. With on-demand throughput, DynamoDB instantly accommodates your workloads as they scale up or scale down to any previously reached traffic level. If a workload's traffic level reaches a new peak, DynamoDB adapts to accommodate the workload. Tables that use on-demand mode deliver the same single-digit millisecond latency, service level agreement, or SLA, commitment, and security that DynamoDB already offers. You can choose on-demand mode for both new and existing tables, and you can continue using the existing DynamoDB APIs without changing code. DynamoDB On-Demand offers pay-per-request pricing for read and write requests, so that you pay only for what you use. On-demand mode is a good option when you create new tables with unknown workloads. You have unpredictable application traffic, or you prefer the ease of paying for only what's used. We'll now go through an activity to calculate the RCUs and WCUs needed for a workload. We will go through a read scenario and a write scenario. Suppose you need to read 20 items every second. Each item is 11 kilobytes in size, and you are using eventual consistency. How many RCUs must you provision? Remember that one RCU provides one strongly consistent read or 2 eventually consistent reads per second, and each read is limited to 4 kilobytes in size. Pause the video for a minute and see if you can calculate the answer. When you are ready to compare your answer, resume playing. If your answer is 30 RCUs, congratulations! Now here's how to get that result. First, round up the read size, 11 kilobytes, to the next multiple of 4, that's 12 kilobytes. Now divide the read size of 12 kilobytes by 4 to get the RCUs that you need per read operation. The result is 3 RCUs per read operation. We need to read 20 items per second, so multiply 20 by the number of RCUs per read operation. This results in a total of 60 RCUs. However, the scenario asks for eventually consistent reads, which means we need only half the number of RCUs. So 60 divided by 2 gets us to the final answer of 30 RCUs. Now we'll calculate the number of writes necessary for a workload. In this scenario, you need to write 120 items per minute. Each item is 7 kilobytes in size. How many WCUs must you provision? Remember that one WCU provides 1 write per second for items up to 1 kilobyte in size. Pause the video for a minute and see if you can calculate the answer. When you are ready to compare your answer, resume playing. If your answer is 14 WCU, congratulations. Now here's how to get that result. First, each item is 7 kilobytes, which means 7 WCUs per item. We need to read 120 items per minute, so divide 120 by 60 to get 2 items per second. Then multiply 7 WCUs by 2 items per second to get a total of 14 WCUs. Here are the key takeaways for this section of the module. DynamoDB provides two read consistencies. Eventual consistency means data might be stale, and strong consistency means data is up to date. DynamoDB transactions offer insert, delete, and update operations that are all or nothing and ACID compliant. And read and write throughput can be either provisioned, meaning set throughput, or on demand, which means changes with demand. That's it for this video. Thanks for watching. I'll see you in the next video. Section 7, Streams and Global Tables. Applications can benefit from capturing changes to items that are stored in a DynamoDB table at the point when these changes occur. For example, consider an application that makes changes to user preferences, which are stored in a DynamoDB table. Another application, such as an advertisement server, must respond to the new preferences and present different advertisements. You can enable DynamoDB streams as a solution for this use case. This optional feature captures a time-ordered sequence, which is called a stream, of item-level modifications in any DynamoDB table. This information is stored for up to 24 hours. Applications can view the original and modified data items in near real time. A stream consists of stream records. Each stream record represents a single data modification in the table the stream belongs to. Each stream record has a sequence number reflecting the order in which the record was published to the stream. When an application creates, updates, or deletes items in the table, DynamoDB streams writes a stream record. It records the primary key attributes of the items that were modified. You can configure the stream to capture additional information, such as the before and after images of modified items. Stream records are organized into groups or shards. Each shard acts as a container for multiple stream records, and it contains information that is required to access and iterate through these records. The stream records in a shard are automatically removed after 24 hours. In the slide example, an update is made for Jane's favorite exercise. When this occurs, DynamoDB asynchronously writes an update to the stream and tags the record with a sequence number to ensure proper ordering. Records are then grouped into shards. Subscribers can then consume the shards to monitor changes to the table. You can use global tables to keep DynamoDB tables synchronized across AWS regions. Global tables provide a fully managed solution to deploy a multi-region, multi-active database without needing to build and maintain your own replication solution. When you create a global table, you specify the AWS regions where you want the table to be available. DynamoDB performs all the necessary tasks to create identical tables in these regions and to propagate ongoing data changes to all of them. Suppose that you have a large customer base spread across North America, Europe, and Asia. When customers use your application, they must update their profile information. You could create 3 identical DynamoDB tables named customer profiles in 3 different regions. These tables would be entirely separate from each other. Changes to the data in one table would not be reflected in the others. Without a managed replication solution, you could write code to replicate data changes among these tables. However, this could be a time-consuming and labor-intensive effort. Instead of writing your own code, you could create a global table that consists of your 3 region-specific customer profiles tables. DynamoDB would then automatically replicate data changes among those tables. Thus, changes to the profile data in one region would be propagated to the other regions. In addition, if one of the AWS regions becomes temporarily unavailable, your customers could still access the same profile data in the other regions. A global table is a collection of one or more DynamoDB tables, which are called replica tables. A replica table, or replica, is a single DynamoDB table that functions as a part of a global table. Each replica stores the same set of data items. Any given global table can only have one replica table per region. Each replica has the same table name and the same primary key schema. Global tables use DynamoDB streams to propagate changes between replicas. Any changes that are made to any item in any replica table are recorded in a stream. These changes are propagated to all the other replicas in the same global table. In a global table, a newly written item is usually propagated to all replica tables within seconds. With a global table, each replica table stores the same set of data items. DynamoDB does not support partial replication of only some of the items. Conflicts can arise if applications update the same item in different regions at about the same time. To achieve eventual consistency, DynamoDB global tables use a last writer wins reconciliation between concurrent updates. DynamoDB makes a best effort to determine the last writer. With this conflict resolution mechanism, all the replicas agree on the latest update. Then they converge to a state where they have identical data. When you read from global tables, you must consider what consistency you require, eventual or strong, when choosing a replica to read from. If you need a strongly consistent read, you must read from a replica that is in region. DynamoDB does not support strongly consistent reads across regions. The slide shows two read operations, one within the same region and the other across regions. A strongly consistent read is possible in US East 1 because the database and replica are in the same region. However, the read operation from US West 2 will be eventually consistent. By default, transactions are disabled on global tables. You can enable transactions on global tables by request, but replication across regions is asynchronous and eventually consistent. You might observe partially completed transactions during replication to other regions. Here are the key takeaways from this section of the module. DynamoDB streams are observed changes in data. Streams are composed of shards of data. Streams can be consumed by other AWS services like AWS Lambda, and global tables replicate DynamoDB tables across AWS regions. That's it for this video. Thanks for watching, and I'll see you in the next one. This video covers part 1 of section 9, Basic Operations for DynamoDB Tables. 4 types of basic operations are available to use with DynamoDB. Control operations are the first type and are used to create and manage tables. These operations also provide the ability to work with indexes, streams, and other objects that depend on tables. Data operations are the second type and are used to create, read, update, and delete items in a table. The majority of work done in DynamoDB is with data operations. Some data operations can also be used to read data from a secondary index. Batch operations are the third type and are used to run multiple operations against DynamoDB. Transaction operations are the last type. These are used to make coordinated, all-or-nothing changes to multiple items, both within and across tables. We'll walk through examples of operations in the next several slides. Create table is an asynchronous operation that creates a new table. When DynamoDB receives a create table request, it immediately responds with a table status of creating. After the table is created, the table status is changed to active. You can perform read and write operations only on an active table. You can optionally define secondary indexes on the new table as part of the create table operation. The example on the slide shows how to create a table using the AWS SDK for Python, which is called Boto3. The operation creates a table named users. The partition key or hash key is set as a username, and the sort key or range key is set as last_name. The attributes are defined as string values, and the provision throughput is set to 5 RCUs and 5 WCUs. Now that we have a table, we can add items to it. The put item operation creates a new item or replaces an earlier item with a new item. If an existing item in the specified table has the same primary key as the new item completely replaces the existing item. You can perform a conditional put operation to only add a new item if none of the existing items has the specified primary key. A conditional put can also be used to only replace an existing item if it has certain attribute values. To continue with the example from the previous slide, after the users table is created, the put item operation is invoked to add a new item to the table. The item value is set to the map value of the attributes and values to be written. Use the update item operation to update an existing item's attributes or add a new item to the table if it doesn't already exist. You add, set, or remove attribute values. You can also perform a conditional update on an existing item. For example, You can replace an existing name-value pair if it has certain expected attribute values. In the example, the update_item operation is used to modify the age attribute of an item in the users table. Use the delete item operation to delete an item in a table by using its primary key. You can perform a conditional delete operation to delete an item if it has an expected attribute value. In the example, the delete_item operation is used to delete the Jane Doe item from the users table. For the put item, update item, and delete item operations, you can specify a condition expression to determine which items should be modified. If the condition expression evaluates to true, the operation succeeds. Otherwise, the operation fails. For the slide example, suppose you need an operation that unlocks an account by setting the account locked value to the letter N. However, you do not want this operation to run if the user had a failed login attempt in the previous 24 hours. To do this, an update item operation is used. The optional condition expression specifies the condition to check. The account locked attribute is only set to N if the last failed login attempt was more than 24 hours earlier. That's it for this video. Thanks for watching, and I'll see you in the next video. This video covers part 2 of section 9, basic operations for DynamoDB tables. Use the getItem operation to retrieve a specific item from a DynamoDB table. You must specify the table name and full primary key, the partition key and sort key if it exists. By default, all attributes of the item are returned. You can optionally specify a projection expression to retrieve only certain attributes. You can also request that the operation use a strongly consistent read instead of the default, eventually consistent read. In the slide example, the getItem operation is used to retrieve an item from the users table, which is then printed to standard output. The expected result is a JSON object that contains all of the item's attributes. Use the query operation to read only the items in a table or secondary index that match the primary key. The primary key is specified in the key condition expression. If a filter expression is specified, the query operation returns a result set with only the items that match the specified conditions. If none of the items satisfy the conditions, the operation returns an empty result set. The example uses the query operation to retrieve all items in the users table with a primary key value equal to John Doe. Queries are efficient because DynamoDB will only read items that match the key query condition. The scan operation is similar to a query operation, but the scan operation reads all items from the table or index. You can use a filter expression to refine the result set. In this example, the scan operation is used to retrieve all users whose age is less than 27. Because the scan operation reads all items from the table or index, it's an expensive operation. It's more efficient to perform a query operation using the key condition expression to return only the data that your application needs. If you must do a scan operation, perform a parallel scan when possible. When you run a query or scan, limiting the amount of data returned can improve performance and optimize cost. DynamoDB uses pagination to limit the amount of data, and you can also use the limit parameter. By default, DynamoDB divides the results of query and scan operations into pages of data that are 1 megabyte in size or less. A single query or scan will only return a result set that fits within the 1 megabyte size limit. An application can process the first page of results, then the second page, and so on until the final page is reached. You can also use the limit parameter to limit the number of items that a query or scan returns. Set the limit parameter to the maximum number of items that you want. You can use batch operations to achieve higher throughput by writing, deleting, or replacing multiple items in a single request. You can also use batch operations to take advantage of parallelism without needing to manage multiple threads on your own. You can also achieve lower average latencies compared to using single put item or delete item operations when multiple items are written, deleted, or replaced. The batch getItem operation returns the attributes of one or more items from one or more tables. You identify requested items by primary key. A single operation can return up to 16 megabytes of data, which can contain as many as 100 items. The batch write item operation puts or deletes multiple items in one or more tables. A single operation can write up to 16 megabytes of data, which can comprise as many as 25 put or delete request. Individual items to be written can be as large as 400 kilobytes. With batch operations, if one request in a batch fails, the entire operation does not fail. You can use the DynamoDB transactional read and write APIs to manage complex business workflows. These workflows might require adding, updating, or deleting multiple items as a single all-or-nothing operation. For example, a video game developer can ensure that players' profiles are updated correctly when they exchange items in a game or make in-game purchases. DynamoDB has two operations to handle transactions: transact write items and transact get items. The transact write items operation contains a set of write operations with one or more put item, update item, or delete item operations. The operation can optionally check for prerequisite conditions that must be true before any updates are made. The transact get items operation contains a set of read operations with one or more get item operations. If the operation is issued on an item that is part of an active write transaction, the read transaction is canceled. Here are the key takeaways for this section of the module. DynamoDB has four basic operations. Control operations are used to create and manage tables. Data operations are used to create, read, update, and delete data. Batch operations are used to read and write multiple items. And transactional operations are used to coordinate all or nothing changes to multiple items. That's it for this video. Thanks for watching, and I'll see you in the next one. Time to review the module and wrap up with a discussion of a practice certification exam question. In summary, in this module, you learn how to recognize different database options on AWS, identify the features of DynamoDB, describe the components of DynamoDB, explain how DynamoDB uses partitions, indicate how indexes are used with DynamoDB, describe how DynamoDB keeps data consistent, recognize when streaming and global tables are used, explain the backup and restore process, and develop with DynamoDB by using the AWS SDKs. Now let's take a look at a sample exam question. A developer is creating a solution that will use an Amazon DynamoDB table. Anytime the table is updated, the changes must be sent to AWS Lambda. Lambda will then send a message to the operations team when certain values exist. How could the developer modify the table to create the solution? A. Create a global secondary index to speed up queries so the developer's code can get faster results. B. Create a local secondary index to speed up queries so the developer's code can get faster results. Or C. Enable DynamoDB streams on the table. D. None of the above. Note the key requirements stated in the problem. The solution must use a DynamoDB table, and when the table is updated, the changes must be sent to AWS Lambda. Consider the answer choices and rule them out based on these key requirements. We'll pause a few seconds before discussing the correct answer. If you need more time to consider the answer choices, pause the video. So how do these answer choices compare to the requirements? The purpose of a global secondary index is to help speed up queries of non-key attributes. But this would not help the developer immediately notice updates to the table. A local secondary index would provide the application a choice of sort keys to run query or scan requests. However, this would also not help the developer immediately notice updates to the table. With DynamoDB streams enabled, the developer could set the table to emit new images to the stream, which could be associated with the Lambda function. This would meet the requirements. Because we've seen that option C meets the requirements, the answer isn't D, none of the above. The correct answer is C. When DynamoDB streams is enabled, the table will emit one of four options to the stream: keys only, new image, or new and old images. The developer could select the new image option, which writes update information to the stream. This stream could then be associated with the target Lambda function. The function would receive update information, which it could use to determine whether the operations team must be notified. That concludes this module. Thanks for watching, and see you in the next video.